Hello everyone and welcome back to another mini concept, this time about Hess's Law, the last topic we're going to be covering on enthalpy. So Hess's Law covers multi-step reactions, and multi-step reactions are, as the name suggests, reactions that lead you to a certain point, however it takes multiple steps to get there. So imagine going from point A to point B, but there's stairs in between. These stairs, every step on the stairs are a step in the multi-step reaction. Now, what does Hess's law state about the enthalpy of this process, this entire process? Essentially, we want to get from A to B. That's our main goal. So we want to get the enthalpy of A to B, getting from A to B. Now, there's also energy being expended or added on each step of the reaction. Obviously, when you're moving down the stairs, you would need to exert energy to put your foot on each step. So there's enthalpy on the first step, enthalpy on the second step, enthalpy on the third step, until eventually you're at the destination, which is B. Essentially, what it's saying is that the total enthalpy of the process is equal to just the sum of the enthalpies of each step of the reaction. So on and so forth. So the total enthalpy is equal to enthalpy 1 plus enthalpy 2, so on and so forth. Now, the solving of this is it's more on a visual process rather than purely numeric, and I'll explain that in a while. This is because Hess's law states that essentially in a multi-step process, it doesn't matter how you get to where you want to go. It just matters that you get there. And that's true even in real life. It doesn't matter how many stairs or escalators you have to go through. You're still going to end up at the same place if you go fast or if you go slow. What matters is where you are going to end up. And in Hess's law, for multi-step reactions, we have a certain process to follow. So first is we have to find our goal or the destination. So find the destination. Finding the destination is our first step. Find the end or goal. Okay, so for example, here in this first Hess Law problem that we're going to be doing, we want to end up with this reaction. So our goal here would be to have 2-methyl propan 1-ol, which is C4H10O, and we want it to decompose into C4H8 or 2-methylpropene plus and water vapor. So we want to make sure that this reaction is our end goal, right? And what are the steps to getting here? It says here that these are our steps. The carbon reacts with hydrogen gas and oxygen gas, and it produces our 2-methylpropan 1-ol. And eventually, the next step would be to have more carbon react with more hydrogen gas, and it forms 2-methylpropene. And the last step would be to have hydrogen gas react with oxygen gas to form water vapor. Now, we order these based on where we want our final substituents to be placed. Now, what does that mean? Okay, so for example here in our first equation, let's see if I can have good handwriting for this one. So we can see here that it's not in the right order in terms of where the 2-methylpropan 1-ol is located. Okay, so hold on, let me just finish drawing the reaction. Okay, there. So here in our end goal, the 2-methylpropan 1-ol is supposed to be on the left, right? And right now it's on the right side of the reaction. It's a product. We want it to be a reactant. Now, how would we fix that? How do we put it in the right spot? Well, obviously, the only way to do it is if we flip the equation around. So since we have all of these on the left, we have to put them on the right. And here, this is our new revised first step. So this is the first step of our chemical equation or our chemical process to get us to what we want. Now, how about the enthalpy? The original enthalpy of the first step. Now, in the first step, it said that the enthalpy was negative 335 kilojoules per mole. Right? So, negative 335 kilojoules per mole. Now, we flipped the reaction though. So that means that instead of actually releasing energy, we produce or absorb more energy. And we can see how that's true because this time, instead of forming bonds, we're actually breaking bonds. And if you recall in the last video, bond breakage is endothermic and bond formation is exothermic. So since we're breaking bonds here, we're going to have an endothermic reaction and we're going to flip the sign. So instead of having it be negative, we'll be having a positive enthalpy. So I hope that's clear so far. Now, how about the next step? Now we can move on to the next step because we have our primary substituent here on the right side now. These other substituents, they're not exactly very relevant to our end goal, so we don't really have to pay much attention to them yet. Okay, now how about the second step? Our second step was 4 carbons plus 4 moles of hydrogen gas. They turn into 2-methylpropene. So that's C4H8. Now, are they on the right side? Okay, so these characters or these substituents of the reaction, they're not exactly relevant. What we're more concerned with is this one, which is 2-methylpropene. So we want to make sure where is the 2-methylpropene in our end goal. Our end goal, it's on the product side. Is it on the product side here? Well, it is. So that means that it's on the right spot. So we'll give this another color. We'll give this yellow. So this is already correct. So that means we don't do anything to our enthalpy. So the enthalpy here is going to remain the same. It's going to be negative 17. These are all in kilojoules. Forgive my bad handwriting. Okay. Right there. Hold on. There. Okay, now how about the third step? The third and final step. So we have hydrogen gas, we have half a mole of oxygen gas, and it turns into water vapor. So where is water vapor in our end goal? It's on the product side. Is it on the product side here? Yes, it is. So that means that everything here is fine. So our enthalpy for the last reaction is going to be, or the last step rather, is negative 242 kilojoules. Now, what do we do from here? Hold on, let's move this. Okay, so now that we have this, well, why did we do all that? Why did we have to reorder all of these steps? And why is it important that we do this before we actually start adding the enthalpies? Well, it's simply because if we're going to go down the stairs, we have to go down properly and not skip any steps or accidentally be going back up. We want to make sure that if we're going down the stairs, it's not 2 steps forward and 1 step back, rather all the way down. If we want to go up, we want to go all the way up and not 1 step backward. So here, when we flip this part of the equation, this part of the multi-step reaction rather, we made sure that we're going in the right direction. If we weren't going to flip it, it kind of doesn't make sense, because how would we decompose 2-methylpropan-1-ol into whatever we want it to decompose into if we don't put it in the right spot? Alright, so now that we've established that, what's the next step? So the next step is really quite simple. All we have to do is cross out or cancel out similar substituents across the multi-step reactions. Now, what does that mean? So these similar substituents are basically like terms across the chemical process. And literally by across, I mean across. So when, for example, here we have a carbon on the product side and we have carbon on the reactant side. These are on different steps of the reaction, but they are across each other. They both share the same amount of moles, so we can cancel them out. So cancel. Oh, oops. Okay, so here we can cancel this out, the 4 carbons and 4 carbons here. And how about this one? Oh, oops. I put Yeah, okay. Here we have 1/2 mole of oxygen and then 1/2 mole of oxygen here. So we can cross these out, we can cancel them. Now we have 5 moles of hydrogen gas here and only 4 on this side. Can we cancel that out? No, we can't because they're not the same amount of moles. But wait, we have 1 more mole of hydrogen gas here. Now these two are on the same side, so we can actually add them up together. So 4 plus 1 is equal to 5 moles of hydrogen gas, and we can cross out our hydrogens now. So now what does that leave us with? So we only have the 2-methylpropan-1-ol on the left side that's not crossed out, and we also only have our 2-methylpropene and our water vapor on the right side. And is that what we want? Yes, that's in fact what we want to end up with. So our final reaction would just be bringing down all of the remainders. We will have our 2-methylpropan-1-ol, and this will turn into our end goal, which was hold on, let me pick out a different pen. This one, our 2-methylpropene, C4H8, and our water vapor. Now, was this similar or identical to what we want? Are these the same? Yes, they are. So that means we did Hess's law correct. Now, again, Hess's law is not just about making stuff match. We also need to calculate for the enthalpy. So what do we do now? We just have to add all of these. Oops, can't really see that, but we just have to add all of the enthalpies throughout the multi-step reaction. So just add all of these together, and we will get an answer of 76 kilojoules per mole. So for every mole of these substances in this ratio 1:1:1, we would have 76 kilojoules per mole produced, and that's the same for every time this set of reactions happen. So this multi-step reaction happens, I mean. So yeah, that's Hess's law. Now how about another example before we end this video? Oh, that's from the last video. Sorry, let's move this over here. Okay. So the compound diborane is used as a rocket fuel, and the equation for the combustion of diborane is shown below. And that's B2H6 plus 3 moles of oxygen gas combust with 3 moles of oxygen gas to form B2O3 and 3 moles of liquid water. Now, how do we get the enthalpy of combustion? Well, here, we just use Hess's law again, because clearly, we have a Hess's law problem. We have 3 steps in this reaction. So what do we do first? Again, we have to find our goal. So what's our goal? Our goal here is to achieve this reaction, right? So we'll have B2H6 plus 3O2. This turns into B2O3 plus 3H2O. So we want to make sure that our final answer, once we're done canceling everything out and once we're done adjusting the enthalpies and etc., we want to make sure that they all match up to this main reaction. So now, how do we do it? Again, we'll start with the first step on the reaction. So let's use the green pen. The first step of our reaction is 2 borons react with 3 moles of hydrogen gas to form B2H6, which is diborane. B2H6. Now, which one here are we most concerned with? Boron and hydrogen gas are just substituents. They're not exactly very special, but what's special in this first step? What's special in the first step is diborane, because it's present in our final goal. So what do we have to do? It's on the wrong side. It has to be on the left. So again, we're going to flip our reaction. When we flip the reaction, we're just going to put everything that was on the product side to the reactant side. I'm gonna put it right there. And now what happens to the enthalpy value? Well, our enthalpy, or originally it was positive 36. But again, what happens to enthalpy when we flip a reaction? From 36, it becomes negative 36. right? And we can see that that makes sense because we're reversing the reaction, and yeah, that's it. So this is one of those reactions where it doesn't follow exactly the bond breakage and bond formation rule that I mentioned earlier, because this time it has an assigned value for enthalpy. So it's always important to analyze first before making assumptions using the knowledge that you already know. So now, next, we're good with the first step. So now let's move on to the second step. The second step is hydrogen gas reacts with 1/2 mole of oxygen gas to form liquid water. Now, where is liquid water in our final goal? Liquid water is on the right. Okay, so that's good. It's on the right spot. But it only produces 1 mole of water. Now, that might be a bit of a problem because as you can see here in the third step, just peeking forward, we don't have any more water being formed. So how will we manage to get 3 moles of water from just 1? It's not like we can just randomly spawn water from thin air. Well, easily, what we can do here is just multiply the entire reaction by 3. So in that sense, we'd be multiplying our enthalpy as well. So our enthalpy would be 3 times negative 286. And we would be multiplying 3 to everything here. So 3, 3, and 3. Now, we would have the right amount of waters produced. So 3 times 1 is 3 moles of hydrogen gas. 3 times 1/2 would be 3 halves of oxygen gas, and then this would form 3 moles of water. So what's our final enthalpy for this part of the reaction? It would be 3 times 286, that's negative 858 kilojoules. Hold on, let me fix the formatting of this because it's kind of ugly. Okay, let's move this here. Okay, there. So this is our new enthalpy for the adjusted second step. Now, why did we adjust the second step? Because it didn't produce enough of what we're looking for. It only produces 1 mole of liquid water when we do in fact need 3. And to get the third mole, or to get up to 3 moles rather, we just multiply the entire thing by 3. And because the enthalpy is based on kilojoules per mole, again, based on the ratio of this step, if we multiply the reaction by 3, we also multiply the enthalpy by 3. So now, on to our third and final step. Our third and final step is 2 borons react with 1/2 or just 3 half moles of oxygen gas to form B2O. B2O3 rather. Now, is there anything to adjust here? What are we concerned with? We're concerned with B2O3 because it appears in our final goal. Now, is it on the right side? Here it's on the product side, and on the bottom it's on the product side as well. So that means it's going to be acceptable. Whatever the enthalpy of this is, it won't change. It's going to be the exact same. So we'll have 1,274 kilojoules of energy for this final step of the reaction. That's the enthalpy for the final step. Now, we have no more alterations. We're sure with our constituents, or substituents rather, of the overall process. So now we can start canceling stuff out. So let's start with the first step. What can we cancel out here? We have 2 borons and we have 3 hydrogen gas. So these 2 borons, does it appear anywhere across the process? Apparently, there seems to be 2 borons on the third step on the reactant side, so that means that we can cancel these out. So we'll cancel the borons. Now, how about the hydrogen gas? The hydrogen gas here exists in 3 moles. Is there 3 moles of hydrogen gas on the reactant side anywhere else in the equation? Well, yes, there is. Here in the second step, there's 3 moles of hydrogen gas because we adjusted it and multiplied it by 3. So now we can cancel these out. Now, how about our oxygens? Do we have to cancel anything out for oxygen? Well, no, we don't, because oxygen is in the right spot. We need to have oxygen on the left side. So now that we have nothing left to cancel out and we're completely fine with everything, we just have to simplify whatever we have left. And now that just means bringing down and adding up everything. So here, let's bring down our final equation. Our final chemical equation would be B2H6 or diborane reacting with 3 halves plus 3 halves, that's 6/2, which is also just 3. 3 moles of oxygen gas to produce 1 mole of B2O3 and 3 moles of liquid water. Is this our final goal? It is in fact the final goal. So now what do we do? Well, all we have to do is just add everything up. And when we add everything up, we should have a final enthalpy of combustion, which is negative 2168 kilojoules per mole. And that is how we use or apply Hess's law to get the enthalpy of multi-step reactions. So again, what do we do to solve Hess law problems? First, we have to identify what our final goal is, what the final equation that we want is. So for example, here in this case, it was this one right here, the equation for the combustion of diborane. And next is we write down all of the steps of the reaction and we adjust the reaction based on what we actually need it to look like. We need it to be in the right order from left to right because it's going to be how the reaction evolves or essentially just moves towards the end goal. If it's not going to be going in the right direction during one of these steps, then it's not going to get to the right place. Now, after that, what do? We adjust it also based on how much of our end goal we need. If you see that you're lacking moles of certain substances, then you multiply. You can also divide if that's needed. And lastly, you're going to cancel out substances that are appearing on both sides of the equation or the chemical equation. And then you bring down all of your remaining substances to see if you match your end goal. If you match your end goal, then that just means you add up all the enthalpies that you adjusted or did not adjust. And that will be your final enthalpy for that problem. So yeah, Hess's law is really more visual rather than math heavy. And it's also slightly analytical because you need to understand which substances you want on either side or just in general which you're trying to get to. But overall, with practice, this will definitely become a lot easier and you can actually find a couple of shortcuts to make your life a lot easier regarding this topic. So yeah, that's all, and I hope that you guys learned something from this video. So I'll be covering the next topic in Gen Chem 2, which is entropy, in the next video. So entropy, microstates, and eventually Gibbs free energy are going to be a few of our next topics on the Minute Concepts channel. So thank you everyone, and I hope you guys learned something again, and I'll see you in the next video. Bye bye.